Hello everyone. If you're watching this, you missed day 2 of our week 3 Foundations of Tech lecture. Let's get to it. So we are continuing where we left off, talking about Ohm's law, meaning of voltage, resistance, and current, which we'll get a deeper understanding of today. And I'm hoping you can create your own basic series and parallel circuits, although we probably won't get to, well, I know we didn't get to parallel circuits today. We'll be covering those next lecture. Today we're talking about series circuits. There are 3 assignments to think about. Assignment 2 was due yesterday, so please make sure you get that to me as soon as you can if you haven't yet. I will try to be harassing you by email about that if you still owe it to me. Assignment 3, electricity concept notes, we went over together in the previous lecture, so if you missed that, please watch the previous video and or send me an email. I'm happy to help you with that, but that is due Friday the 19th by midnight if you need more time to complete it. Assignment 4, we started today and is going to be due Tuesday the 23rd. So if you are confused on it by the end of today, please send me an email and I can help you with that as well. Please don't forget, you will be needing physical supplies for our activities next week. You can pick those up Friday the 19th from 8 to 3, or if that doesn't work for you, you can come Saturday from 10 to noon. I personally will be at the school handing them out. You'll meet me in the middle of the bus loop, and I will be happy to give you everything you need. So consider showing up then if you can't come on Friday. A little stretching warm up. All right, let's get to it. So the first thing I want to talk about today is AC versus DC power. We talked about this a little bit, but we didn't explicitly mention the difference between the two. So DC current, called direct current, is the situation where all the electrons line up in a nice orderly queue and they all go in the same direction. Think of this like a grocery line, right? Everyone comes up to the register all in order and then they go out the door and they're on their way. Alternating current is a little bit different. An alternating current has the electrons go one way, then they go, wait, hold on, let's go back. I forgot something. They turn around, they go back, then they turn around again and go forward, then they turn around again. They continuously do this over and over and over again, going back and forth. They might say, why would they do that, or how would that even work? And wouldn't the lights in my house flicker like this if that was the case? The answer to those questions is, well, first of all, the lights in your house do flicker like this, but they do it really, really fast to the point where your eye can't actually tell. In fact, they flicker 50 to 60 times per second. We call we call that phenomena frequency. We measure it in hertz. So if we take a look at our little diagram here, what's going on is as we spin a coil inside a magnetic field, of course, you can spin a magnet around a coil as well. It doesn't matter which way you do it. The electrons first move one direction as they're attracted by the north field, so they go towards that. But then, as the coil turns around, all the electrons are attracted in the opposite direction, so they have to go back. This happens over and over and over again. In fact, this spins fast enough where this happens 50 to 60 times a second, really fast. Here you can see the voltage. This line in the center is the zero line. At that point, there is no voltage, meaning there's no power. Your light would be off. However, as this starts spinning up, you get a positive voltage. And then as it spins back to zero and spins around, you get a negative voltage. So you get these oscillations between positive and negative voltage, and all that means is which way the electrons are flowing. Are they going clockwise or counterclockwise around this loop here? That's all that's changing. So batteries provide direct current. Electrons just keep going from one end of the battery to the other. Generators, these kinds, provide AC. And of course, we have different appliances that use different types of current, and we have transformers that'll transform it from one form to another. And power inverters take it from DC and turn it back into AC. So there's all kinds of things associated with this that we might or might not get to talk about later. But for now, let's keep going. Let's skip over a couple of things here. Let's talk about the main meat of today. That is, we want to be able to design our own circuits. First of all, there is a application. You can find it on MyMCPS under modules called Circuit Builder Link. If you open it up, you'll get a screen that looks something like this. And this is a really simple environment where you can experiment with some circuits. On the left here, you have some elements you can drag out, like batteries and wires and all sorts of crazy things, like a dog, perhaps, that you can hook up to your electrical grid. Now, you can either leave the view as this, or you can switch it to this, which is what we would call a more engineering-based view. When an electrical engineer draws a circuit, they will use these symbols to symbolize these objects. I'm going to use the regular view for now. Here we have two different ways we can measure something about our circuit. The voltmeter lets you measure the voltage drop from 2 points. The ammeter lets you measure the current, how much charge is flowing across a specific point. So let's get started. We are going to first build what we call a series circuit. Now, something that's really important is your circuit has to be closed. You have to complete the path from the positive to the negative end of your battery. Otherwise, you're not going to get any charge to flow. The second thing to keep in mind is you don't want to create what's called a short circuit. Let me demonstrate a short circuit for you. If you were to, let's say, want to power this light bulb, but you accidentally, when you were going to do it, made this contraption where there's a secondary path for the electricity to go down, as you can see, even though I've powered up this light bulb here, none of these electrons here are moving, and the light bulb does not shine. And our battery is on fire. That seems bad. The reason this happens is electricity is lazy like you guys, right? It doesn't want to do extra work. It doesn't want to go out of its way to find more things to do. Just tries to do the minimum possible. So the minimum possible here is to just go this way. This is a much easier way to go than going through this light bulb, right? So that's how it'll flow. If we take out this middle section, now the electrons are flowing through the light bulb as you would expect, and the light bulb is on. This is what you want to do. You don't want to short circuit something. So it's really important as you build these that you avoid that short circuit situation. All right, so let's keep going. The first circuit we're going to build is going to be a series circuit. A series circuit is like Christmas lights. Everything is connected one after the other. And the electricity must pass through one component to get to the second, to get to the third, and so on. If you take one out, the circuit becomes open and electricity cannot flow. So in your Christmas lights, if they're the old kind, if you take out one light bulb, the whole thing goes out. And the reason for that is electricity can't get through that component anymore. So how do we model a series circuit? Well, let's make one with 3 light bulbs here. So I'm going to put 2 more out. And what we want to do is we want to wire them up in such a way that electricity only has one direction to go, and that direction must carry it through all 3 light bulbs before returning back to the battery, like so. Ta-da! Well, you'll notice that the light bulbs are much dimmer than when we just had one. And the reason for that has to do with the amount of power we're able to get out of this battery. This battery has a certain voltage drop across itself. In this case, it happens to be 9 volts. And we can measure certain things about this particular circuit by using the voltmeter and the ammeter, as previously mentioned. One important takeaway about this circuit is if we measure the current, notice the current is exactly the same anywhere you look. And the reason for that is, look at these electrons. They're all moving at the same rate. Think of this like a pipe. If you change some spot in the pipe, the whole pipe slows down at the same rate. So similar thing happens here. If I was to adjust the voltage here, I'm going to be able to get much more flow. As you can see, I've increased the current to 0.68, but it's going to be the same everywhere. It increases by the same amount everywhere. Now, the second thing you can note about this kind of circuit is the voltage drop. So the voltage drop across 2 points can be measured by placing one of these little diodes on one side and one on the other. And you'll find out how much voltage you have between these 2 points. Here we have 20.5 volts, and that corresponds to what we set our battery to, so that makes sense. Now, something interesting happens if I switch these two. You'll see I still get 20.5, but now it's negative. For our purposes, it's not going to usually matter whether the voltage is negative or positive. It just determines which way the electrons are flowing. So this is telling me the electrons are actually going this way, and I've crossed my wires. All right, so let's look at how the voltage is distributed. If we measure the voltage across this first light bulb, you'll see that the voltage, let's just make it positive here, switching these, is 6.83. Now, something interesting you can do is if you change the resistance, you'll see the voltage drop also increases, and you'll see the other two light bulbs become dimmer. What happens there? Well, let me leave this as a 45 ohm, meaning out of the 20.5 volts I've supplied, 14.2 basically of that is taken up by this light bulb here. The rest of the voltage will be distributed between these other two light bulbs, 3.15 here and 3.15 here, because both of these have the same resistance. So what can we conclude? If we were to add up all the voltage drops across each component, we're going to get the total voltage of our battery, and the greater the resistance of a component, the greater the voltage drop across it. And we can use Ohm's law to calculate all of these things. So for instance, if we wanted to calculate the voltage drop across here, we could use our current and our resistance to figure that out. So this is going to be something we'll be doing in a future lesson. For now, let's take a look at your assignment. So assignment 4, Ohm's law. This is the beginning of being able to use this equation to find out useful information. So if we look at it, I have a bunch of questions, and all of the questions you'll know 2 of the 3 quantities that we can relate using Ohm's law. Please remember that Ohm's law is V for voltage is equal to I for current times R for resistance. So you can use this information to then solve for the missing piece. Remember that voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. Let's do this first one together really quickly. Here we know that we have 0.5 A of current, we have 120 volts of voltage. We want to find the resistance. Find R. Well, let's do it. We can say 120 volts is equal to 0.5 amps times some kind of resistance, ohms. So some unknown R ohms. Okay, well, if we want to get ohms by themselves here, we got to divide both sides by 0.5. Divided by 0.5 A divided by 0.5a. And the reason we're dividing is the opposite of multiplication, which is what we have over here on the right. When we do this, we get a result. 120 divided by a half is the same as multiplying it by 2, so 240. And the units here are going to be ohms. Volts divided by amps give you ohms. And that should make sense to you because resistance is measured in ohms. So there you go. That is how you do number 1. Hopefully you can do the rest of them. If you have trouble, please let me know. And if you haven't turned in past assignments, remember the time is slowly ticking away. The first deadline is going to be March 1st for assignment 1 and March 4th for assignment 2. Please don't forget to turn those in. Thank you very much, and I'll see you next class.